So this is 126. And we're doing analyzing malicious Windows programs. So let's start with that. Oh, I see the camera's not working. Let me see what I can do about that. That perhaps. That. Okay. All right. So the first thing is to talk about the API, which we've already talked about a bit. This is how every piece of Windows software works, is by making API calls and asking the Windows operating system to do things. So there are data types, dword for 32-bit words and word for 16-bit integers. And this Hungarian notation uses DW before the variable name to indicate the size of it. So you got word, double word, handle, and long pointer. A handle is a reference to an object, so something like a file you might open would have a handle pointing to it, or a window, and then you can redirect things you send later to that object. And there's long pointers too. So handles, for every process has a handle, every menu, every file, and so on. And the only thing you do with a handle is when you have an operation that sends data or uses an object, you include a handle to that object. You don't add numbers to them or anything. So create window EX will create a window and then return a handle. And then if you want to destroy it, you call it with the handle so it knows which window you're trying to destroy. And you can create files, read and write files, of course. And here's create file mapping. And map view of files is a more unusual way to load the contents of a file into memory or execute it. And these unusual ways are used by malware, of course, to try to trick antivirus, because the way antivirus works is by hooking these functions. So every time you try to read a file, it will say, wait, I have to scan it first. And so if you use an unusual way to read the file, you might be able to trick defenses into not noticing. These 2 backslashes take you to the root of the system, and 2 backslashes and a question mark are sometimes used too. So this will take you to this is a more direct way to refer to an object on a server, and it lets you have longer file names and sometimes gives special properties like \\\, dot \\, lets you refer to devices directly. And we've talked about this in forensics. If you refer to a device directly, you could image the whole drive, including like the master file table and all the partitions and such, which is giving you more of the drive than referring to, say, a drive letter, which is a partition on the drive, not the whole thing. All right. And the alternate data streams is the rarity of a Windows feature added for compatibility with Apple. Apple was first in providing music to their users, and they would have the name of the music file, and they'd have 2 streams of data. One would be the actual sound of the music, and the other would lead to like cover art and liner notes and such. So Microsoft added this feature so you can define something like foo, and then you can treat that file like a device, like drive C, and you can store more data inside it. foo:\bar.txt will put these 2's inside a file called bar.txt inside, pointed to by the name foo. So the name foo now contains 2 files. Those are alternate data streams, and they're not all that important anymore, but when they were less known about 10 years ago, some antivirus would not scan alternate data streams, and so it was a place where you could hide viruses. Now they're pretty much all onto it. And then there's the registry, which we're going to spend a lot of time going through here. In earlier operating systems like MS-DOS, there were some text files scattered around, and in Linux, the configuration of all software is done by text files all over the place, one of the worst offenders being Apache. If you want to configure an Apache server, there's an apache.conf file, but there are 3 or 4 other places where you can put configurations, and it can be kind of a mess trying to find them all. But that was the old way to do it. You'd have a text file tied to one program, and Microsoft decided they didn't like that, So in Windows 95, they swept all the settings for all the operating system settings and all the software settings into this binary object called the registry, which is a very strange object composed of 5 or more files on the disk piled into a strange tree-structured directory, which is very oddly structured. Parts of it are just redundant of other parts of it. But anyway, the registry is where all your settings go. Everything you set in control panel, the background, the mouse speed, and everything goes in the registry. And you can use the malware, you can use the registry to make things auto-start. So there are the 5 root keys that you see in Registry Editor with these names. As root current user, they call these things a key, even though they look like a folder. And one thing about registry keys is they always have to have a value in it. Even if it is default value not set, they can't have a key without a value. And then you have subkeys or folders within a folder, and each value has a type and data. So there are about 5 types, and this was data not set. So regedit is the main tool you use to view and edit the registry. And there's the root keys. So local machine are settings that apply to the whole machine, and here's settings that apply to the current user. And here's defining types like associating software with file extensions. And the current configuration is the hardware configuration. And here's the settings for all the users. So HKey current user is equal to one of these HKey users, the one that is currently logged in. One interesting use for ADS, the student says, is also used to determine whether the file is coming from the internet or like a local network. Yes, I'm glad you mentioned that. Yes, that's where the tags go that mark this file has been downloaded from the internet, and sometimes you have to go right-click into properties and clear that to run a file. Yeah, that's right. Good. Thank you. All right, so here's the one we use most often in instant response, is the run key. There's a few of these, some for 32-bit and some for 64-bit and so on, but here's the main one. HKey local machine software, Microsoft, Windows, current version, run, and anything in here will automatically run when you log on. So you see various things here like LogMeIn and Adobe ARM and Dropbox and so on that we're running on this machine, like Java updates. All right, so auto runs is the best tool to find out what's automatically launching on a machine. These ways to make a file launch on startup are called auto start extensibility points, and there are a lot of them. The simplest one used to be startup folders, and that's still there. You put a shortcut in the startup folder and it will launch. And the run key comes after that, and there are many, many other ways to make something run automatically. So auto runs is the best tool to find most of them, although there is no tool that can find them all. And so it'll show you a lot of the objects that automatically load. So here's what you'll see. Here's the ones in the run key are ARM and box sync helper. Here's ones in the startup folder. Here's ones in another startup folder. Here's something active setup, installed components, and so on. Another run key. So, various places have various things launching, and you can see them all here. So if here's API calls, this one will open a key. This one will set a value. This one will get a value. So you can read the registry. Those are things you'll typically see. Now, documentation of objects will often omit the W or A. So if you see a call to regopenKeyXW, then the documentation for regopenKeyX would apply. The W just determines whether you want a 16-bit character or 8-bit characters in the strings you're using here. And Microsoft uses both. It uses both ASCII characters and wide characters. And so here's the naming convention. You'll see something like create window and then create window EX, which means it's the extended version of this, because many, many Windows API calls are modifications of ones in earlier versions of Windows. You might even see EX, and then you'll see a W at the end or an A to determine whether it wants wide characters or ASCII characters. That's a good thing to know. And so here is code that modifies registry settings. So you see here it's got a string, which is clearly a registry path leading to the run key. And then it calls regopenKeyXW. So it's going to open this run key, and then it's going to set a value there. And somewhere around here will be the string. I don't see it, but it's just this value name and data. stored elsewhere, but somehow they have a name and the data which should be passed to something. So this is the assembly language that will set a run key to automatically launch something, probably malware. You can also export a whole registry hive, one of the root key or any section of the registry. You choose some object, and then you can export it with file export as a reg file. And the reg file is just a notepad document that lists these keys. You save it as a reg file, and here's what reg files look like. They just have these square brackets delineating where something is, and then you can use reg files to document registry. You can also use them to set registry keys. So this is one simple way to deploy fixes. I've done this, for example, when you don't want a Windows update to go on because you're worried about it. Sometimes there are registry keys that will delay an update, and you could distribute a reg file like this, and then people could just double click on it and it would change the registry, but they'd have to run with administrator privileges. One thing about it is you do not want end users ever going in here. Registry editor is very dangerous. There is no undo, and any change you make here takes effect on the system immediately. This is like opening the hood and messing with the engine of a car while it's running. So you can very easily destroy your machine by making sloppy changes in regedit. So you don't want amateur people going in here. If you want registry changes made by an end user, you should really use a system like run this reg file, so they don't have to actually go into regedit. And of course, you can also deploy these things with group policy, which is even better. Although I'm not sure you can deploy a reg file and run it directly with group policy. I think you can, but I've never tried that, so I can't swear it's going to work, but I think it would work. And I imagine you could do it with PowerShell too, if you wanted to push out a registry change. All right, let's take a look at a Kahoot. Library. 126, 7A. They got the Halloween theme. All right. Well, I guess maybe that's it. Administrators do it all the time for group policy. Thank you. That's good. All right. All right. Which one is a pointer to an object? That's a handle. Good. All right. The second stream of data in a file. All right. That's the alternate data stream. All right, how about a root key? Okay, that's H key current user. All right. And this is internals tool. All right, that's all it runs. Good. All right. I know who that is. I think I know who that is too. All right. Good. So, all right, so here's networking APIs. The basic low-level library called WinSock, there used to be a place called the Ultimate Collection of WinSock software. This is the basis of the internet. The Berkeley libraries defined the basic protocols that are used to make the internet, and Microsoft imported them into Microsoft and called it WS232. So that's the Windows sockets, and this is how you make a network connection in the real old-fashioned way. You use create a socket object, then you do accept to connect to a remote server, and then receive and send, or you bind to a port and then listen for incoming data because you're a server, and then accept. And these are the fundamental operations. This is the old-fashioned way called raw sockets that gives you complete control over networking, and it is very rarely used in Windows software. This is far too much work and far too difficult to set up. The only reason you do this is because you're trying to invent a new network protocol, and most of the time you just want to use some standard protocol like HTTP or HTTPS, and so you don't use this library directly, WS232. You use something like WinINet. But anyway, here's how it works on the server side. You would create a socket, then bind a port to it, then listen, and then accept a connection, and then send and receive. If you're phoning out to a server, then you do socket and then connect, and then send and receive. And so you'll see that here. You call WSA startup first to get it ready, and then you have socket, bind, listen. This is the sort of thing you would see in assembly code showing the API calls. And if it's good software that isn't going to just crash, then it should be using WSA get last error to check for error conditions. If you use a shellcode that you get from, say, Metasploit, it doesn't do this, and it will just crash if anything goes wrong. But most software wants to be more robust than that, and so it would be checking for errors and handling them gracefully. So WinINet is the high-level API that a normal developer would use. They would not waste their time with WinSock. And now you can call things like Internet Open, Internet Read File, and so on, which does something meaningful and obvious and handles all the details. An executable, yes, if an executable is using WS232.dil, that is suspicious. The most normal reason you would do that is because you have actually imported software from Linux and put it in Windows, which is, I think, how it originally worked, all this WinSock software. That was why they used it. I'm guessing about that. I'm not sure, but I think that's the reason. But yeah, nowadays, I think there's no reason for anyone to use raw sockets like that unless they're doing something very strange. And the most likely reason is they're malware. They're just trying to avoid doing the obvious thing to avoid getting caught. So if then, of course, you want to transfer execution from one part of code to another, jump and call will move to another part of code and stay there, but there are many other ways. And we'll talk about these. These are the main ways malware runs. With DIL injection, where they move in a library. So we'll talk about these objects, processes, threads, mutexes. All right, so DILs are the main one. Microsoft uses dynamic link loading. So it loads libraries from separate files when you launch a program. And if the library is already in RAM because somebody else loaded it, it just connects to the running copy of that library. And this makes code smaller and makes it load faster, but it's dangerous and unsanitary because Windows does not verify the integrity of those libraries. That is considered to be a process that is too much burden on the system, so it doesn't really verify that they're signed, and Microsoft doesn't even sign all the system DILs, and it doesn't even check to make sure they're coming from a good folder and not from some other folder. So this is the main way malware gets on systems, is you trick it into loading a malicious DIL instead of the real DIL, which we've done quite a bit in the projects. So static linking is the other way to do it, where if you include a library in your program, you put an entire copy of the library in your executable. So if I'm using networking, my executable has my own copy of the networking stuff, and another executable using networking has its copy, this means that there's more wasted RAM as 2 copies of that library are up there, but it also means I didn't have to trust some other source for code that the developer did not include. But I don't think anybody uses static linking on Windows. I've never seen it. It's not common at all anymore. So that's the advantage. Makes code smaller, and it also means you can combine software. You can reuse code from other people. They make a library. You can buy libraries that do things, and so on. But you can put malicious code in DILs and then trick a process into loading it. You can use typical Windows DILs to do things. This is living off the land where you use the built-in tools to do things. And you can use third-party DILs. If you have a program that is installed on many machines like Firefox, you can use its libraries to do whatever you're doing, just assuming Firefox is installed, which it probably is. That's another way to get things done. So a DIL is just like an exe. There's just a single flag in the portable executable header to tell you that it's a library instead of an exe. Executables have exports and imports. The only thing an executable exports is typically start or main, but it imports a lot from DILs. The only difference about DILs is they have more exports, where they offer more ways to enter because they're offering a variety of functions. DIL main is the main function of a DIL, and when you first load it, it automatically runs DIL main to prepare the DIL for use. That's why Metasploit malware puts the malicious activity in DIL main. So all you have to do is import the library, and that will run the malware. You don't have to actually call any functions in it, and it doesn't even need to offer any functions to have malicious effect. Everything is a process, every program being run, and it has its own handles and its own memory, and the processes are broken up into threads. The threads are pieces of code that can proceed independent of other code, so if one of them ends up waiting for something slow, like user input, the other parts can move ahead. And the process, the CPU time is assigned by threads. So Microsoft is a threaded multiprocessing system. I think it's multiprocessing. It might be with multiple processors. Anyway, you can run many programs at a time, and each program can run many threads at a time. So if you go to Task Manager, you'll see many processes all running at once on your machine. And of course, the processor can only do one thing at a time, unless you have multiple processors, which a lot of people do now. And so it's really giving each one of these a few cycles, and this one a few cycles, and that one a few cycles, jumping through all the threads to give the illusion that they're all moving, but they aren't all moving. All right. So each one of them has its own memory region. We've seen this when looking in OllyDebug. And if two processes think they're using the same memory address, like most executables think they're loaded at 400,000, but they're not. That's a virtual address space. They're actually all loaded in different physical RAM. So you create a process with create process, and then you can specify the input, output, and error streams, and even you can connect input and output to a network socket, and then you've got a remote shell where this process will take data from the network and send data out the network. And that's what you find in shell code. So here's code to create a shell, get a socket handle, and then call assign standard error, standard output, and standard input. Here they are, loading these, and setting them all the same, it looks like here, which I don't quite understand, but anyway, then, all right, load them into this LP process information data structure. And now there's a command line here that you push up, and then you call it. And so it will now create the process by running this command line and then using input, output, and error as specified in that other place. The fact that those are all set the same makes me think that this might be something that is not going to have any input or output, that they're all just going to be throwing it away, but I'm not quite sure. All right. So the process is a container that contains threads, and the threads are what actually moves as the processor gives them threads. There might be only one thread in a simple process, but other processes will have a variety of them. And each thread has its own registers and stack. And it has a thread context. So when you move to another thread, it has to save the context in a structure called the thread context, and this is called a context switch. So you can call create thread to create a thread. And malware might load malicious DIL in the process by using create threads, one for input and one for output if you want to communicate. Mutexes are much easier to understand and commonly there. Mutexes are just objects in the file system that are handles, and you can put it in the file system and they can be seen by many processes. This is how you perform inter-process communication. So if your two processes are sharing some object, like a file, I'm writing to that file, and I don't want the other process writing to that file until I'm done, then I would put a mutex up saying, I'm writing, wait till I'm done. And malware often creates a mutex just to mark the machine as infected, so that when the malware gets run another time, which is quite common because the user fell for a phishing link and they might fall for a phishing link again or run the executable again thinking something is wrong, then you don't want to reinfect the same box, so it looks for the mutex. So here's some functions for it. Wait for single object will give a thread access to the mutex, and then release mutex will say when you're done. You can create a mutex this way, and you can open it. So this is how you refer to a mutex, so you can have code that checks to see if there's a mutex, and that tells you something like don't do this until that mutex vanishes. So to make sure only one copy of malware is running, this stuff opens mutex, then it compares it to this name, and it opens the mutex, tests to see if it exists, which is here, and if it does exist, it leaves and does nothing. If it does not exist, then it creates it with this HGL345 name. That's the idea. All right, so 7B is here. All right. All right, I think that's it. All right, which library has bind and accept? Those are raw socket calls in WS232. Which library has internet read file? Yep, WinINet, good. All right, which one is a type of file differing from an exe by one flag? That's a DIL. Good. And which one is the global object used to coordinate processes? That's a mutex. I've heard it also called a mutant. There is some difference, but I forget what it is. For all practical purposes, they're the same thing. All right. All right. All right. So services are programs that run and do not deliver anything to the user. They are there to help other sources, other programs do things. They're like the libraries, but they're running processes. They're not just files on the disk that are loaded only when needed. And so here's one that's running called App Host Service, Application Host Helper. And here's Windows Audio Endpoint Builder. Some of them are running, others are stopped. Some of them launch only when needed. So in practice, they end up quite a bit like libraries, but they're technically different inside. A lot of them run as system because a lot of services have to be running before you log in. And before you log in, it can't run with your account yet because you haven't authenticated to identify who you are. So it can only run with internal accounts, and there's a few of them. There's a network account, network service, and local system is the highest one, and there are a few others. A lot of services run as system. So they can run automatically when Windows starts, and therefore this is a nice way to gain persistence, is to just start a service from an executable that you have loaded, and that's another way to make things launch at startup. So there's a service control manager. You can contact it with the API, you can create a service, and you can start a service. And when you create it, you can specify whether it automatically launches at boot or not. There's a variety of boot options for it. SVC host is the main executable used to launch services. Many services are all using the same SVC host executable. And these series of registry keys list the groups of services to be launched with SVC host. And when you go into Process Explorer, you'll see all these pink SVC hosts. And if you hover over one, it will show you these are the network restricted processes, which is Windows Manager, network connections, offline files, and these are registry settings. There's a registry key that lists all the members of this group, and the group is launched as one process here, and there are many groups. So a lot of your Windows system is actually running in these SVC host processes. So there are own processes that run in an independent process, and there are kernel driver processes that run with ring 0 privileges in the kernel, and those are, of course, high privilege device drivers that come from the people that make devices typically. And Microsoft requires them to be signed these days because they're really tired of buggy device drivers causing a blue screen of death. So here's an example of the information in the registry. So here I am in local machine system, current control set services, browser. And in the browser container, there's landman server, and there it is, the browser process. All right, and it's got types here. This is a Win32 share process because it's a type 20, which is set in here somewhere. Down here, the last one, type 20. All right. You can also control this from the command line with the SC command. So here's SC querying the browser process, and this showed me the information by looking at the registry for the browser process, and this shows me the same information in the command line. I did a query about the browser process, and here's that type 20 and all the other information about it. And here's the path name. This is just going to launch the network services. So it is included in the network services, and probably a lot of other things are too, and this is the command line that launches it. The component object model is yet another way for code to be shared by other processes, which again accomplishes approximately the same thing as a service or a library. It's just another way to do it. So COM objects have to call OLE initialize or co-initialize before they can refer to other COM objects, and they are accessed by globally unique identifiers, which are 128-bit numbers like IPv6 addresses. As you can tell, this is the Windows theme, many ways to do essentially the same thing, and it comes from history. These things were brought in through different paths, and now all these different ways of doing things are supported in Windows. So there are class identifiers and interface identifiers for these COM objects. And I'm not sure that's COM object. Those are types of identifiers. These things are, by the way, these things that are called globally unique identifiers are the same on every machine. So it keeps with the Microsoft tradition that the name of everything is always the opposite of what it is. They are totally not globally unique. All right, so exceptions are conditions caused by illegal operations. So if you divide by 0 or you try to execute a ring 0 command with ring 3 privileges or something like that, that creates an exception. And the exception interrupts the flow of code and then goes to an exception handler, which decides what to do about it. If you're running in a program, it goes to the structured exception handler, where your program may have specified code to run when an exception happens to handle errors gracefully, which is what professionally written code should do. So it's going to have the information put in fs:0. Fs is a segment register that points to the exception handler. So here it is putting a address in there to load the exception handler. All right. And if you take 127, we develop exception handler exploits. There are overflows in memory corruption attacks that can alter the contents of the exception handler, and it's one of the many ways to obtain code execution on Windows machines. So kernel mode is ring 0 here with full privilege to run every instruction the processor can execute, and ring 3 is the only other mode that's used, called userland, which is not allowed to execute certain instructions that are considered too dangerous. And in general, the ones you can execute in kernel mode that you can't execute in user mode are the ones that directly touch the hardware. So if you want to print something on the screen from user mode, you are not authorized to do it. You have to call a API call that will go down to the kernel mode and ask the kernel to please put that on the screen for you. These rings 1 and 2 are used by old, long-forgotten operating systems like Minix, but they're not used by any modern operating system, not Linux or Windows. So user mode is where everything you run, you see it in Process Explorer at the bottom, everything you launch from the desktop or a command prompt after you log in, it runs with your privileges, and it is not in kernel mode. All right. And the only way your user mode programs can manipulate hardware is through the Windows API that ultimately goes down to kernel structures that are written either by Microsoft or by the device makers who wrote the device drivers. So you have user mode processes. They each have their own memory and resources. If your user mode process crashes, it doesn't bring down the entire operating system because it can't affect the kernel. It just causes that one process to stop, and now the kernel is still running, so Windows can still recover and put up an error message or something. You can't jump directly from the user mode to the kernel. You have to call these commands, sysenter, syscall, or int2e, execute a jump to kernel. Those are system calls, and it uses lookup tables to locate certain predefined functions. There's a parameter when you do this, and you give it in EAX, you have a number, and it looks up the function you're calling from that number. But you don't jump directly to a kernel address. You jump to a predefined list of addresses. So kernel processes are all mixed together, which is an amazing thing. About 10 years ago, I was researching some stuff, and I came across an attack that would cause a blue screen of death on Windows machines. And people said, I said, how can this be? And they said, all you have to do is send enough IPv6 router advertisement packets. It makes the kernel busy, and they say if a kernel process uses up all the RAM, the operating system will just crash. And I said, you got to be kidding. They said, no, that's the way it is, and here's this book telling me the same thing. Kernel processes don't have security checks. They aren't isolated from each other. They just share resources. If any one of them does anything invalid, the whole OS just crashes. And this is why in older versions of Windows, everybody and their brother was putting code in the kernel. Antiviruses, firewalls, rootkits, drivers, and Microsoft kept on getting stricter and stricter about the quality of code going in the kernel, because any bad code in the kernel just causes the whole machine to die, and everybody blames Microsoft when they see the blue screen of death, even though most of them are caused by non-Microsoft code in the kernel. So Microsoft has gotten ever more and more strict that the code in the kernel has to be verified by Microsoft, meet certain standards, and be signed to make sure it's not been modified. So you can put kernel mode malware in earlier versions of Windows, although since about Windows 8 or Windows 10, this has seemed to be almost impossible. They made it much more difficult to sneak malware into the kernel. The only kernel mode exploits I'm aware of recently are ones where you find a valid signed piece of code from a real manufacturer that happens to have a vulnerability, and then you exploit it. But putting your code in the kernel is almost impossible now. Microsoft has a lot of defenses, as far as I know. If somebody knows a way to do it on Windows 10, I'm interested. Anyway, rootkits used to use kernel code all the time. Most malware runs in user mode only. All right, so the native API is ntdil. Here, your user application is up here. Your user application normally calls kernel 32. Again, remember the rule for Microsoft, everything is named the opposite of what it is. Kernel 32 is not the kernel, and it is not running in kernel mode. It is your gateway to the kernel from userland. And it doesn't even go directly to the kernel. And kernel 32 goes to ntdil. ntdil is the code that makes the jump to the kernel mode, and this is considered the native API, which is somewhat undocumented and is considered to be only for internal Microsoft use. That's the native API. Kernel 32 is what they want you using. So this is the same thing we talked about, WinINet and WS232, and also about control panel and regedit. There is a powerful but dangerous tool available that Microsoft does not want you to use, and there is the expected way in. Like, you're supposed to use control panel and not go right into regedit, and you're supposed to use WinINet and not go straight to WS232, and you're supposed to use kernel 32 and not go straight to ntdil. This is the native API. This is the API with friendly functions that Microsoft wants you to use. And so, of course, malware often skips across this and jumps straight into the native API, both to gain access to those powerful functions and also to just be unexpected, so malware detection engines that hook kernel 32 API calls will not detect it. And by the way, the kernel is this, ntos kernel.exe. All right. So that's undocumented for Microsoft use, and it can be more powerful. The normal way would be to go from kernel 32, the normal way we go to kernel 32 to ntdil to the kernel. Just what you see here. This is the normal flow. Yeah, I remember, why did Bill Gates regret using Control-Alt-Delete? I remember hearing that, but I forget the answer. I remember hearing that maybe 15 years ago. I don't know. It is kind of a screwy thing, really. You could just have an on button, you know? I don't know why he did that. Attackers, yes, a cat will skip kernel 32 and call directly to ntdil. That's right. You run around here. That's what you do. And then you have to write more difficult code using these some undocumented features, but it's possible that you'll skip some anti-malware processes. Exactly. And so your security program, if it's hooking these calls up here, then by jumping straight down here, you will bypass it. Yes, I would say using ntdil directly is suspicious. It is not normal for user application to call ntdil or use it. What it should do is call kernel 32. So again, just like we said, calling WS232 would be suspicious. Calling ntdil function directly would also be suspicious. Not impossible. It might be, because there's some people just like to do things the hard way. Like Steve Gibson said recently, he writes all of his code in assembly language. Can't be bothered with BASIC or C++ or anything. So people like that might just go right down here as a matter of style, but it is not the normal practice. So here's some API calls. Here's NT calls, query system information, query information about threads and keys, and these are much more powerful than the high-level kernel 32 calls. You can get much more information about the details of the system from the native API. And here's NT continue to return from an exception, so that can be useful. Some malware makes it very hard to follow it by using strange ways to jump from one part of it to another, and one way is to trigger an exception and have an exception handler take over. All right, let's take a look at 7C, which is here. Analyzing a network program used high-level calls. You would not see bind and socket and all that. That's correct. If you called a WinINet file, like internet read file, that's all you would see. You would not see the bind or other low-level calls. It would not be in the code written by the developer. That would be implemented by the WinINet functions, which you wouldn't probably see. Remember, we talked about this in IDA Pro. There's the blue stuff and the yellow stuff. The blue stuff is the user land, and you would not find any ntdil reference there. It would be referenced in, I think, the yellow stuff, the library code, where you normally don't look because that's written by Microsoft. And most of the time you're looking for the behavior of malware written by a developer, not looking for bugs in Microsoft code, unless you're trying to earn a Microsoft bug bounty or something. All right. All right. Is the user account more powerful than the administrator? That's it. System. That's the all-powerful account. Can do things like read the password hashes, which the administrator cannot do. All right, what service loads ring 0 code? Yeah, the kernel driver loads kernel code. All right. Services are not necessarily running in kernel mode. All right, where's the native API? ntdil is the native API. All right, if you divide by 0, what happens? It creates an exception, and it goes to the exception handler, the structured exception handler. All right. All right. All right. Well, I'll stop this one.